record it. This is lecture lecture 9, right? So if you remember, we were discussing stability of f of x, and if we were able to choose a v which was positive definite, and if v dot is negative semi-definite, then it is stable, and if v dot is negative definite, then it is asymptotically stable in that domain D, right? So this is what we were doing last time. We did an example also, a couple of examples, right? And if we can show that our v is radially unbounded, right? Radially unbounded. I don't know if you remember the definition. I think radially unbounded was v goes to infinity if x goes to infinity, right? Then if this is true, then it is globally asymptotically stable gas, right? Globally asymptotically stable if your Lyapunov candidate function is radially unbounded. And I think we did example, if the x equals to infinity means for all the different cases, so like v is infinity only if x is infinity, and there were several cases like there were some examples. I think 1 over 1 plus x 2 square or something was there where this thing goes to infinity when what was that example? So I think something like this: x1 squared over 1 plus x1 squared plus so on, to give that radially unbounded example. So there's an additional condition on V, which yeah. So this x1 square plus x2 square thing, if this v of x, what do you say, is it radially unbounded, this example here? So I know if so let's see, v of x I can write as, if I take x1 square outside, it will be 1 over 1 plus x1 squared, right? It will cancel out from the top. If I just take out x1 squared common from here and here, it will, I can write it like this, right? Now if I say if x1 goes to infinity and x2, what happens when x1 goes to infinity? That means norm, let's say norm is x1 square plus x2 squared. That's a norm, right? Second norm of x, mod of x can be. But let's say x1 goes to infinity, not the x2, and let's say x2 is any constant value or something. Then this goes to 0, so it becomes 1, right? 1 plus 0, 1. So even though your x, mod of x went to infinity, this v of x did not go to infinity unless x2 goes to infinity. So this means it is not radially unbounded. Means the figure will look something like this. Like it has circles like this, and this, and then the curves will start opening in this direction. So this is x2 and x1. So x2 it is curves will be, but here after some time this becomes this kind of opens up. There are no closed compact sets. Do you remember our solution where we said that we could make an in the proof we had this omega beta things like that, right? The energy level curves, and in that curve if you are there you will not get out of that curve. So those were closed and compact sets. But if you see here, after some time I will not be able to make those closed and compact sets. It kind of opens up. So if a function is not radially unbounded, then you cannot take that closed and compact set and extend it to the whole space. It will open up somewhere. Yeah. So that's the logic here. So the energy level curves after some time in the direction of x1, because when x1 goes to infinity, the energy curves kind of opens up here, and I won't be able to make some kind of a closed and compact set omega epsilon or omega beta where I can say if your here energy is negative semi-definite. So the additional condition of radial unboundedness, if you can show that your function is a function like this, half x1 squared plus half x2 squared, this is radially unbounded. Anything goes to infinity, either x1 goes to infinity or x2 goes to infinity or both goes to infinity, that means the norm goes to infinity, this function also goes to infinity. Then in that case your energy curves are like this. You have closed compact set and it will keep increasing as you go in both x1 and x2 direction. But if a function is not radially unbounded, then something like this will happen and it will open up and then you will seize. So you can still prove asymptotic stability in this domain, right? But you cannot say that, one cannot comment about global asymptotic stability, that you start anywhere and you will come to the origin. That is not good. To guarantee that, your Lyapunov candidate function should be radially unbounded. Okay, so that's the kind of extra condition you have for radial unboundedness. And last time we did two examples, right? We did inverted pendulum example where, if you remember, like our x1 dot equals to x2 and x2 dot equals to minus a sine x1 minus bx2. So this is an example of inverted pendulum. And if we took two types of Lyapunov candidate functions, right? One was v equals to a1 minus cos x, cos x1 plus half x2 squared, right? For that your v dot came out to be minus b x2 square, I believe. Yeah. So this is what? This is negative semi-definite, right? So this, if you want to do, you have to understand these definitions of what is semi-definite and indefinite. If those definitions are clear, then it will make much more sense because that will govern your transition from stability to asymptotic stability. Okay. So this is a negative semi-definite function because for negative definiteness it has to be 0 when only if x is 0. x0 means both x1 and x2 0. But this goes to 0 at x2 equals to 0. So that means it is not negative semi-definite. So all you can show is that this, it enters a set. If it starts in a set, it will never leave this set, but there is no way you can say that. Okay, but I know that this system is asymptotically stable, right? So the Lyapunov condition candidate function that you chose here was not sufficient to show. So you have to choose another Lyapunov candidate function. I think if you remember, we did an example. Second, we chose this v equals to half x transpose px plus a1 minus cos of x1, right? So there p was p11, p12, p12, p22. So basically the whole idea was this has to be positive definite and v dot has to be negative definite, right? So to show that, at the end you have flexibility to choose p11, p12, p12 to p22, right? Such that this is PD and this is negative definite, and we were able to show that, right? If you do that, then actually it was a negative definite thing, and that means it was asymptotically stable. So this is a hard thing, because sometimes you will not get a proper Lyapunov candidate function. What should we do? So, but later on we will have this Lassalle's invariance principle that we will do, which will, even if we have this condition, we will be able to show that it is asymptotically stable. Even with negative semi-definite property, we will be able to show that it is asymptotically stable. Okay. So now for example, if you take a linear system, right? I don't know if we did this in the modern control class. So let's say we have x dot equals to ax, right? And if you remember the Lyapunov condition of stability, for one was the eigenvalues are negative, of course. If A has negative eigenvalues, then system is asymptotically stable. The other condition was, if you remember, was that there exists a P matrix which is positive definite, A transpose equals to, we satisfy this equation, Lyapunov equation, for any cube, positive definite cube, any positive definite cube. There is a solution to P, then the system is asymptotically stable. So how did we do that? So let's say, so that was the condition of stability. Let's see if it satisfies the Lyapunov theory. How did it came actually? So the idea was, let's say we start with a Lyapunov candidate function equals to half x transpose px, because, and P is a positive definite matrix. If it is a positive definite matrix, it satisfies all the conditions of positive definite, right? This is always positive, V is always positive, and it is 0 only at origin. Means all the x's are 0. When I say 0 at the origin, means origin all x1, x2, x3, x4, x5 equal to 0. So it is only 0 when all the variables are 0, otherwise it is not 0, right? So that's good. So if we find v dot, what is v dot? Del v by, so del v by del x into x dot, right? Is transpose into x dot. So that will be, v dot will be, first we take, so it will be half x transpose dot px, and then half x transpose p x dot, right? In this case, and both so now we can plug things in. So now if you plug things in, what is x transpose dot? This will be x dot is ax, right? So x dot transpose is x transpose a transpose, so it will be half x transpose a. In fact, you don't need half for that, that is also still a positive. X transpose a transpose px plus x transpose p ax, right? Now you can take out x outside this side, so we have x transpose this side in both the quantities here, right? So it becomes a transpose p plus pa into x, right? And now we know that it is equal to minus q. We started with that condition, right? This a transpose p plus pa equals to minus q. So if I plug in that, it becomes minus x transpose q x. And we know that q is a positive definite matrix. What does that mean? X transpose q x is, which is v dot. This is v dot, right? So it is not equal to, this negative. It's negative definite. That means system is asymptotically stable. So you can see that you don't need eigenvalues if that's how the Lyapunov equation came by. So for the linear system. Questions? Let's see if we have any other. Okay, so now we move to that invariance principle theorem that I was talking about. So this is called Lassalle's invariance principle or theorem. Okay, so let's start with this example. X double dot equals to minus alpha x dot minus beta x, okay, where alpha and beta is greater than 0. So we have equation it's a second order integrator, right? It's a second order integrator. So how would you, first thing is to put it into state space form, right? How would you put that? You can choose x1 equals to x and x2 equals to x dot. Then equations of motion will be x1 dot equals to x2 and x2 dot equals to minus beta x1 and minus alpha x2, right? No problem, right? So let's start with a Lyapunov candidate function. What will be like? Okay, your guess. Suggest a Lyapunov candidate function for this to start with.
1/2.
V equals to 1/2 x square, x1 square plus 1/2 x2 square, right? Simplest Lyapunov candidate function to start with. Okay, so we can find v dot. V dot will be x1 dot plus x2 dot, right? Is that clear? This what I do differentiation here. So basically, whenever let's say I have this, right, v, how do I get this equation from here? So I'm doing a partial, right? When you do a partial of this is 2. So we have 1/2. You take a differentiation with respect to x1, it is 2x1, right? And then you multiply it with x1 dot also with respect to the time, because it is del v by del x into x dot. So you do it for each quantity. So this becomes x1 dot, this becomes x2 dot, and if we see, then what is x1 dot? It is x2. X1 dot is x2, and x2 will be minus, if I multiply this with this one, it will be minus beta x1 x2 and minus alpha x2 square, right? Huh? No, it's no transpose needed. Now, one more logic you see, when I chose this simplest candidate function, I'm not able to cancel this and that, right? It's supposed to be cancelled. That will be good. This is an indeterminate term. So if you think I multiply this thing by beta, right? If I multiply this by, was it alpha and beta? That's what I chose, right? Or you can, means, right? If this was beta, what will happen? If I chose this to be half beta x1 square, then there will be a beta here. What happens? So that's the logic. Like when you choose a Lyapunov candidate function, always keep that flexibility that multiplying to a scalar is not it does not violate any rule. It is still positive difference. So then that cancels out, and then you are remaining with minus alpha. See, our objective is to cancel terms which are indeterminate, so that you can make a conclusion on it. So it comes out to be alpha x2 square, and alpha is positive, x2 square is also positive. So this is, we can say that v dot is less than equal to 0, negative semi-definite. So we can reach at a conclusion that at least it is a stable system, right? Okay. There is no denying that, right? It's a negative semi-definite. So you can show that, at least you can say that. Now, but let's investigate, because somehow I know that this system is asymptotically stable. So either you go ahead and go back and find a better Lyapunov candidate function, a more general one, and maybe not guaranteed that you will be successful in showing negative definiteness. But you can do a simple test. So this shows that if that means v dot equals to 0 where? Because ultimately, if everywhere else except at x2 equals to 0, this is negative. So if we have this x1 and x2, right? Or this is x2 and x1, so x2 equals to 0 is what? This line here, right? This is x2 equals to 0 line. So at this line, v dot is 0, right? That means the energy stops changing. Anything other than that, it is negative. That means mostly it is pushing things like this, right? So that's why that is what is happening. So x2 is going to 0. That's what. But let's see at x2 equals to 0 what happens. So when x2 is 0, can we say that x2 dot is 0? Can we say that? Anything constant, x2 equals to 0 means it becomes constant. Not even 0, let's say it goes to 3 or 4 or whatever. That means x2 dot is 0. So let's plug in the value. So this is our equation, right? So we say x2 dot equals to 0 means minus beta x1 minus alpha x2 equals to 0. Now this is 0, right? x2 is 0. So we are saying that x2 dot cannot be 0. This whole thing cannot be 0 until unless x1 is 0. This is not even possible, right? So what is happening is, by this logic, that physics of the system is telling us that system is asymptotically stable actually. Okay? So going x2 equals to 0 implies that x1 has to be 0. Finally, this solution will converge to the origin. There is no other set than x1 equals to 0 and x2 equals to 0 where this is met, this condition is met. Okay, so this is a very simple way of showing. There can be bigger problems like this, that's the case. So based on this, there is a guy called LaSalle, and he made our life more hard. And so we'll give next theorem will be for this LaSalle guy. Okay. So let's see if I can explain this. So generalization of this idea is called LaSalle's invariance principle. Okay, so let's see. So we need some definitions for it. Okay, so we'll say that let xt be a solution to x dot equals to f of x. So this is always we are talking, right? We are always talking about solution of x of t. So a definition, a point P is said to be a positive limit point. So a positive limit point of x of t. So we are talking about a point P, which is, we are saying it's a positive limit of this x of t here, x of t, if there exists Tn such that when Tn goes to infinity, x of Tn goes to P. So basically I'm saying that x, point x, right, there is a limit to that point x. So if I take t to infinity, for that x of t converges to that point P, right? So let's say that's here, I start here and then this is P. So when t goes to infinity, this x of t will go here. In positive, because the time scale is positive. You are going from 0 to infinity. Okay? So we are describing because we want to show that the origin is the, this is where it converges. So that's why this definition is important. So x of t is a series, right? It's a data point. If you have data point, and when t goes to infinity, this point, the x of t converges to a point. Okay, so that point is called, I'm not saying if x of t converges or not, but a point P is the definition. If it happens, then that point P is the limit, positive limit point. Okay. Next definition, the set of all positive limit points is called positive limit set. Now it can happen that there are several of such points. Like it may happen that now trajectory doesn't matter where it starts, it converges to the set. Right? So we can have P1, P2, P3, there can be multiple points. So the set of all positive limit points is called positive limit set. Okay. Now, like for example, example can be this. Let's say a point starting here, a point starting here, all converges to this line, right? So this line is basically a set of all those positive limit points. A circle, right? I go there, so basically this circle is also a set of those positive limit points where the line is the x of t is converging, right? So now another definition, a set M is said to be an invariant set if x of 0 belongs to M implies that x of t also belongs to M for all t in R. Okay, so you're saying that if I have a set, right, which is M, and it's just the new definitions of concepts which we learned, like if you are here, you never get out of this set, then that M set between any time, like whether time was negative or time was positive, you are there in that set M. Then that set is called invariant set, right? And if you do a slight twist to this definition, if M is positively invariant, if x of 0 belongs to M implies that x of t also belongs to M for all t greater than equal to 0. So if you're going in a positive cycle, we call it positive invariant set. Mathematicians have, generally for us, positive invariant set makes sense because we don't know the negative time concept, right? So, but I think for mathematicians it is very particular which direction you are going. So for us, every set will be a positive invariant set because time is greater than t0 or 0, right? Again, what set? You are in that set, so the trajectory never leaves that set, basically. That set is positive invariant set. Okay? Now, man. Again, another definition. This is all definitions we are cooking up to explain the Lassalle's invariance principle. Okay? So, bear with me. So there is another thing called distance. Distance to a set. So if I say there is a point P here, right? What is the distance to this set? There is a set and I want to find distance from it. So it's defined like this. Distance to a set can be measured by, we can denote it by this thing called distance rho comma p comma m. So there are two inputs, right? One is the point P and the set M which you are trying to find the distance. So you call it P comma M is infimum. So infimum is the lowest upper bound, if you can think of that. Okay. So it's not minimum, but minimum maximum bound. If you have a time varying. So infimum x belongs to M of P minus x. So basically shortest distance. In other words, it means the shortest distance to any, so there can be thousands of points on this, right? So whichever point gives you the shortest distance, that is the distance. That's how we say that's the distance to that set. Like for example, we have path error we find, right? The path error is always the shortest distance to that path. So you draw a perpendicular, that is the shortest distance, and that's how you define distance. Okay? So when I say another definition, when I say x of t approaches M, what does that mean? It means as t goes to infinity. So there is a point, let's say x of t, and I'm saying this guy goes to M, approaches M, right? As t goes to infinity. What does that mean? That means the distance is decreasing, right? If for all epsilon greater than 0, there exists a t greater than 0 such that distance x of t comma m is less than epsilon for all t greater than t. So what does that mean? That for let's say I'm starting here, right? So let's say I'm starting here, that means the distance is, let's say, epsilon distance, right? So for this epsilon there will be a time interval, capital T, for the, like, how far you start. Depending on how far you're starting from the set, you have a finite time in which the distance will be less than where you started. Exactly, right? So when that's the approaching means, when I'm approaching to a particular point in the space, every time distance is decreasing basically. That means it is always less than where I started, and that epsilon will keep going to zero, right? And keep decreasing. That means I'm approaching that set. All mathematical way of saying that I'm going towards that set. So, okay. So having said that, there is a lemma, I think, here. Lemma 4.1, I think. So lemma is a, like, it's a nice weather before the bad storm comes. So so lemma 4.1 says if a solution x of t, right, of x dot equals to f of x is bounded and belongs to D for t greater than equals to 0, then basically what does that mean? If it is bounded, that means it is stable, right? At least. So negative semi-definite is a enough criteria to say that it is a solution is bounded, right? Because it's a solution, right? That means as soon as you show that v dot is negative semi-definite, at least you know that the system is stable and x of t. It's bounded. So that is what it's saying. If it is v dot is negative, it comes out to be negative semi-definite means it is bounded. That means for t greater than 0, then its positive limit set L plus is a non-empty compact invariant set. Now I don't know if it makes sense or not. So what I'm saying is that, let's say you have this D, right? In this D, I show that my x of t, because in this D your v dot is negative semi-definite, right? Because of that, I know that this will not leave this set. So until now we were just saying that, it will keep rotating in this and it never comes out of it. But it's not true. Means if it is bounded, that means it has to converge to a set. It cannot just randomly keep varying and never comes out of it, kind of thing. Even if sinusoidal oscillations are there, it settles down on a limit cycle kind of thing. But it has to go somewhere. It has to converge to a positive. There is a non-empty positive limit set. What was positive limit set? That when x of t converges to point t as ut goes to infinity, right? That means there is a non-empty. If that is the case, that means something is there. I don't know how big that is or how small that is, but there is a invariant set where it has to go. It's not that it randomly will be doing something. It has to. Its positive limit set L plus is a non-empty compact invariant set. Invariant set also, like, when it goes inside this, then it will never come out of that M. Furthermore, right? So if you remember the definition, moreover, x of t approaches L plus as t goes to infinity, and that's true by definition, right? That's the so if in this D it is stable and bounded, that means it will somehow converge to this non-empty set, positive invariant set M. Okay, so we'll see how it applies to that LaSalle, but that's the lemma. We will not do the proof and all, but we'll just keep it there. Okay, so that we can move to controllers and we can apply these things rather than being entangled in the proofs. But it's important. It will make your life easy. This. Okay, you understood, right? What was that? Just very simple. If in D, V dot is this negative semi-definite, that means there will be a non-empty positive invariant set M, where x of t will approach to this set, basically. And what we will show from LaSalle's invariance principle, that set, if there are certain conditions satisfied, then it is the origin. In that case, boom, that means it is asymptotically stable kind of thing, right? So if you can show that non-empty set is origin, then your job is done. Even if it is negative semi-definite, we have shown that non-empty set is the origin, and solution converges to the origin, even if it is negative semi-definite. That's the part we have. Okay. So theorem 4.4. Okay, it is the LaSalle's invariance principle. LaSalle. So most of the time you will have to invoke this, right? Because you don't want to waste your time in finding a Lyapunov candidate function which shows negative definiteness. Maybe it is good enough to show it is negative semi-definite and then apply LaSalle's invariance principle on it and then say origin is that set where, okay, LaSalle's invariance principle theorem. Okay, so it says let omega subset of D be a compact set that is positively invariant. Now everybody knows, right, what is positively invariant. Positively invariant is a set where if you start, you don't get out of it. Positively invariant with respect to x dot equals to f of x, then we say let a Lyapunov candidate function v d to be r continuously differentiable function such that v dot x is negative semi-definite. So we are now saying, okay, things are negative semi-definite. If you are able to choose a candidate function which is continuously differentiable and v dot x is negative semi-definite and in omega, okay, let E be the set of all points in omega where v dot x equals to 0. Okay, so E, in our case, if you remember our pendulum example where v dot x was what, minus alpha x2 squared, right? If you remember the previous example. So where is v dot x equals to 0? At x2 equals to 0. So that means E is x2 equals to 0, right? Whole line of x2 equals to 0 is E. So there is a set E where basically v dot x is 0. In this case, v dot x equals to 0 at x2 equals to 0, right? Okay. So you can easily find that out, what that E set is, and then let M be the largest invariant set in E. And this E, now in this case there is one E, x2 equals to 0, right? But there can be cases, examples where there is a origin is, so for example, let me tell you, there will be an example, some problems where this is where v dot x equals to 0, right? And there will be a case where v dot x equals to 0 at origin also, right? There will be certain examples where there are multiple, so E is everywhere, wherever v dot x is 0, and there can be multiple disjoint sets, right? One, a circular trajectory, a straight line, origin. In this case, the straight line is, if you see straight line, that means this point is also the part of E set, right? The origin is also part of the E set, but you're saying what is the largest invariant set? Invariant set is different than the whole x2. In this case, invariant set, if you remember, what was the definition of invariant set? That if you go inside that, you don't come out of it, right? You stay there, right? And E is not the invariant set. E is just the place where v dot x equals to 0. We are not saying that if you are in E, you will stay there. But within E, there can be multiple sets, and which one is the largest? In case which one is the largest invariant set? I am saying that this is a part of E. This is also part of E, and both are invariant. Tell me which one is the largest invariant set. The circle, right? Not the origin. So you will see that if that happens, trajectories will go to the circle, not stay on the circle. So the theorem says, let M be the largest invariant set in E, then, this is the theorem statement, then every solution starting in omega approaches to M as t goes to infinity. Got it? So what it is saying that, okay, negative semi-definiteness, we start with negative semi-definiteness, right? And then find E where v dot x is 0. And then in that E, find the invariant sets, largest invariant set. And it is saying that the solution will approach to M as t goes to infinity. And if you can show that largest invariant set is origin, then game over. Then job done. That means system is asymptotically stable, right? So as long as we are able to show that M is nothing but the origin. Okay. So proof is there, but let's just.
So that's the case regardless of what the distance is to, like for example, if the initial condition or whatever, this trajectory solution, the x of t was actually closer to the origin, the trajectories will still end up at the circle
bigger,
because
yes.
it's
Yep.
interesting.
Yep.
Okay.
Exactly. Okay. So that's the case exactly. So there's like what I have said, we can say it in words now. So another corollary 4.1. Corollary. So here we just saying that it goes to largest invariant set, right? So corollary 4.1 says that let x equals to 0 be an equilibrium point, because stability and asymptotic stability are properties of equilibrium points, right? Equilibrium point. You have to go? Is it exercise or let's wait.
May I have your attention? May I have your attention, please? An emergency has been discovered in the building. Responsible personnel are responding.
Okay, guys.